So this is a joint work with my student Wahab and my postdoc Jun. Unfortunately, neither of them could be here today. Wahab has problems getting a U.S. re-entry visa. Jun just had a baby. So in the last 10 years, we have seen a really phenomenal widespread of so-called smart devices around us, like smartphones, tablets, wearables, things like that. Any device that has the label smart probably has a Bluetooth unit in it. Last year, about 3 billion Bluetooth units have been shipped worldwide. Because Bluetooth was primarily designed for personal devices, it's not surprising many applications around Bluetooth are actually privacy sensitive, including car connectivity, health monitoring using wearables, mobile payment, and so on. It often makes newspaper headlines that some hackers can hijack your car or hack into your appliances through Bluetooth connections. So any security vulnerability of Bluetooth can actually cause major concerns on user privacy breach. As a matter of fact, Bluetooth standard does include an encryption feature. Unfortunately, there have been many known attacks on this mechanism. For example, some work show that if you can sniff the pairing process of 2 devices, or if you can capture just the modest amount of traffic, you actually can crack down the encryption. More recently, it was shown that even without the encryption, just looking at the traffic pattern of Bluetooth device, you can tell a lot about users' activities. So all these attacks are actually based on some sort of traffic sniffing. So here we ask the question, is the current Bluetooth technology secure to traffic sniffing? So before I answer this question, let me give you some background. So one of the mechanisms used by Bluetooth that are relevant here is called frequency hopping. The basic idea is to divide a frequency band at 2.4 GHz into 79 channels and hop among them at a frequency about 1600 Hz. So the idea here is to deal with the interference at 2.4 GHz, primarily from Wi-Fi networks. So here shows an example. I'm sorry. Okay. So here shows the example. So the hopping sequence is 2 to 27 long and repeats itself in about 20 plus hours. This entire sequence is solely dependent on the MAC address, which is either public or can be attained with some known techniques. In order to sniff traffic, we have to know the sequence, which actually can be hacked, and the current hop index, which is also called a logic clock value. Fortunately, this is actually a secret value shared between 2 paired devices. So this secret clock value presents the first challenge to traffic sniffing. What's more challenging is a mechanism called adaptive frequency hopping. Here is the example. We have a hopping sequence here. Suppose we have interference on channel 40. So Bluetooth will remap this bad channel to a clear channel to hop to. This remap function is dependent on MAC address and clock value. So what's interesting here is that the details of this implementation is entirely up to the vendor. The standard does not specify how to classify a channel into bad or good. So this means at runtime, a Bluetooth device not only modifies the sequence based on dynamic channel condition, but also will use proprietary algorithms from vendor. So this really raises the bar of traffic sniffing, because in order to follow the traffic, you have to know the MAC address, clock, and remap function. On top of that, you have to know whether the device will stay on the current channel or hop to a new channel. Just a quick recap. Traffic sniffing for Bluetooth has been considered a challenge because of the following reasons. First, the clock value is a secret. Okay. That means we don't know the next hop. Second, the adaptive frequency hopping implementation is up to the vendor. which is not known to sniffer. As in designing any wireless receiver, interference always works against us. Even we can follow the hopping sequence of Bluetooth, the packets we sniff may be corrupted by interference at 2.4 Hz. Because of these challenges, current Bluetooth sniffers either pair with the target device, which really does not fit into the scenario of malicious sniffing we talk about here, or use some sort of broadband reduce, which look like this. So the question we ask here, is it possible to design a practical sniffer using off-the-shelf portable Bluetooth platforms? So we present Blue Ear, which is a practical sniffer using two redos. The first redo is called Scout. So the job of this redo is to figure out the hopping sequence, while the second redo, Snooper, will follow the sequence and capture the packets. So in the following, I will focus on the design of Scout. So the first thing we need to do for Scout is to figure out the secret clock value. So here is the example. This diagram shows a basic hop sequence, which we actually can derive based on MAC address. Now, we stay on clear channel to capture packets of Bluetooth. Suppose we capture 3 packets. In order to figure out the current clock value, we just match the captured packets to the basic hopping sequence we calculated offline. So suppose we have we match the segment here. Apparently there's a mismatch. If we slide to this to the right, here we actually get lucky. We have a perfect match, which means this might be a correct clock value. But you may realize that we may have multiple matches at different clock values. And the idea is to accumulate enough packets so that we actually can eliminate this, all these incorrect clock values and identify the single unique correct clock. So this brute force-based method actually won't work for adaptive frequency hopping. This is why. Suppose we have a hopping sequence and we monitor channel 79. When there is interference, say on channel 40, Bluetooth will remap this channel. So it happens to channel 79 we are monitoring. When there's interference on multiple channels, we may end up with multiple remapped channels, which means we have a lot of mismatches. So the brute force clock matching algorithm won't work. However, the good news here is that Bluetooth standards specify a lower bound on the number of channels you have to hop on, okay, which is 20. Means if you have the entire hopping sequence, on average, the number of mismatches will be no more than 59 over 79. Okay? So this seems to be a good insight we can apply. But the problem here is that in order to use this threshold, you have to have a large number of packets. So that takes a lot of time. So the solution here is the online algorithm. So basically, every time we capture a packet, we update the mismatch ratio for every possible clock value. And then we apply a probabilistic hypothesis testing algorithm. Here, the hypothesis being if the channel is bad, the mismatch ratio will be higher than 59 over 79. Okay? And we repeat this process for every packet we capture until there only one clock remains, which is the correct value we find. And we have evaluated the delay of this process in the paper, but I will skip the details. So the second challenge we need to address is to classify a channel into bad or good so that we can figure out the remapped channel. So this is a simplified logic of Bluetooth packet transmission. First, the device will sense the channel. If the channel X is clear, it will go ahead and transmit. Otherwise, you'll remap to a clear channel Y. Sorry, that's a typo. So the trend here is that channel sensing algorithm is actually not known to us as the sniffer. It's really up to the vendor to implement this logic. So our idea here is to observe the packet reception statistics on the channels and then try to reverse engineer the channel sensing algorithm. Okay? So here are some examples. So this is real data we measured on different channels. So you can see clearly some of the channels actually are not frequently used by Bluetooth because there's interference and they are remapped to new channels. So based on this data, we can derive a simple threshold that can be used to check whether the channel is good or bad. So this channel classifier is actually very accurate because we do use the output of vendor's channel sensing algorithm, which is indicated by packet reception statistics. And then we reverse engineer the channel sensing algorithm. The drawback here is that we need to accumulate enough packets in order to have accurate classification. So now the second idea is, why not we look deeper into the status of channel and try to emulate the channel sensing algorithm of the vendor. Okay? Actually, there has been many such algorithms in the literature. For example, any CSMA systems will use channel measurements to check whether channel is busy or not before it transmits. So the algorithm we came up here with is based on probability density function of received signal strength, or RSS. So we discretize PDF, okay, and then use them as a feature. So you can see on the left, we have a clear channel. The only peak here is actually noise floor. So on the right, we have interfered channel. So the compared with the packet-based classifier, this algorithm is much faster because we can measure the channel condition pretty quickly. However, it may perform pretty badly, mainly because the channel we measure may be very different from the channel of the target because of spatial diversity, right? So now, these two classifiers seem to have complementary performance, right? So why not we combine them into a hybrid classifier? So here's the details. So first, we measure the packet reception ratio on each channel. Then we classify the channel condition based on the packet-based classifier. Then we measure the channel conditions and use the output of packet-based classifier as ground truth to train a SVM algorithm. Okay. So we can do this because the output of packet-based classifier is pretty accurate. Okay. And when the confidence of SVM is low, we always fall back to the packet-based algorithm. Now, the last challenge we have to address has to do with interference. This is actually very similar to hidden terminal problem. See, we have a Wi-Fi AP centered at this particular frequency, which will cause a lot of interference on sniffer. Because of spatial diversity, it may not be a problem for the target. So as a result, the target will continue to hop on these frequencies while the packets we recapture will be corrupted. So to address this challenge, first we monitor the performance of sniffing. When we see a lot of bad packets, we actually jam this channel, okay, to drive the target away. So as a result, okay, the target will only hop on the channels that are actually clear to us. So the reason we can do this is because we use two redos, remember, right? So first redo, which is Scout, can work in parallel with the capturing redo, which can actively jam the channel. We have implemented Blue Ear on two Ubertooth redos, which are basically open source Bluetooth redo platforms. During this process, we fixed a number of bugs of Ubertooth firmware to improve the real-time performance. To test the performance, we used over 50 Bluetooth devices from various vendors. we evaluate the system under both controlled interference and also uncontrolled interference, largely from a Wi-Fi enterprise network. So here we show the packet capture rate. So you can see that at different locations of the site, we can consistently maintain over 90% of capture rate, even with interference from a co-located Wi-Fi network. So as a comparison, the algorithm that only follows a basic hopping sequence actually performed pretty bad. So this plot shows the performance at different distances to the target. So we actually can capture most of the packets even up to 20 meters away from the target. So this is important for privacy sensitive applications because Bluetooth is usually considered short-range technology, but sniffing is actually possible from a certain distance away. So in addition to the design of the system, we also discussed some countermeasures to sniffing. But because of time limit, I will skip the details. I just want to point out the countermeasure we implemented very simple. They can implement it in user space using a simple script. Requires no modification to the device itself. So to conclude, we have designed a system called Blue Ear, which uses two radios to follow the hopping sequence of Bluetooth and capture packets. And the performance we measured using Bluetooth shows that we can maintain high packet capture rate even in the presence of heavy interference from Wi-Fi networks. Traditionally, packet sniffing of Bluetooth has been considered challenging. However, this is not true anymore. We believe this work has important implications for security. So one of the next steps we're doing is to develop simple yet deployable countermeasures to Bluetooth devices. So that's all I have today.